Introduction to PID control is PID stands for proportional integral derivative, and it is a type of device used in industrial application to regulate process variables such as pressure, flow, temperature, and speed. This type of control is used to lead a system to a specific destination. Otherwise, the ground is level. It is almost universally used for temperature regulation and in scientific research. Next is PID control block diagram. A feedback control system is part of a closed-loop system like a PID controller. To create an error signal, this system uses a fixed point to assess the feedback variable. It adjusts the system output based on this when compared to the on-off type controller. However, this controller is steadier and more accurate as compared to on-off type controller. Next is the characteristic of PID controller. First one is proportional control, integral control, derivative control, proportional integral control, and the last one is proportional derivative control.
Selamat sejahtera, my name is Lee Heng. I'm going to present the demo simulations of MATLAB of our group assignments. So the transfer function that we use is second order transfer functions. So this is the coding for our transfer functions. Then there is codings for our value of step response. Then next is the value of gain value of PID controller, which is gain proportional, gain integral, and also gain derivatives. So now let's run code. So there is two figures. So the first figure is used to determine the value of k, l, and t, which is this one. Then, so the step to determine the value of k, l, and t is like this. So this is l, this is t, and also this is k. Next, this is the figure. So next, figure 2 represent the control system of PID, which is closed loop. The step response show it is unstable. Now I'm going to show you the simulating method of our transfer functions. So we're using step to connect with transfer functions for second order, then connected to the scope to observe the output. So this is the simple open loop system of our transfer functions. Then to observe the scope, this is the critically damped response, and then overshoot is 0.502%, and then rise time is 753.905. Next is open loop P controller. We just connect it with the P controller. With the gain is calculated manually, which is 1450.116. So this is the scope of the graph. Same, it shows the critically damped response, and then the overshoot is 0.502, and then the rise time is 753.905. The next is PI controller. Then the proportional gain is calculated manually, and also the integral gain, which is 1350.104, and then 45003.467. So this is the scope, the graph of the output. So it shows it is overdamped, and then there's no overshoot and rise time. For the next is PID. This is the gain of proportional, which is 1740.14, and then the gain integral is 87007, and then the derivative is 8.0007007, and then the filter coefficient we set it as 100. Okay, then this is the scope. Same, it shows the overdamped characteristics with no overshoot and rise time. And then the next is the closed loop P controller. We connect it with a sum with plus minus, and then this is the output. So this show it is an underdamped characteristics. So the overshoot is 42.143%, and then rise time is 33.156. The next is PI controller. So we calculated it manually, same. So the gain proportional is 1350.104, and then the integral is 45003.467. So the scope show it is quite unstable. Then the overshoot is infinity, and then there's no rise time. So the last one is PID controller. Same, the value is calculated manually, and then filter coefficient is 100. So this is the output of the scope. So it shows it is unstable with overshoot is infinity and there's no rise time. Now I'm going to show you the tuning process using MATLAB. So from here, we click P controller. So we click tune. So it will show the result of this graph. So this is the dot graph is show the response of the transfer function before we tune it, and then this is the response after we tune it. To compare two parameters, click here show parameters. So it shows that the block diagrams and the tune response. So we can see that the value of proportional gain is decreased, then the rise time has been increased, and then the overshoot has been decreased. So both graph is stated as stable, but we can see here the graph of Q process is more stable than the block diagram. So next is PI controller. So the same, click here tune. So it shows the result of this graph. So for this case, here stated the closed loop system with controller gains defined in the PID block is unstable and cannot be displayed. So from the graph, from the previous graph is okay, on the previous graph, it is unstable, so it becomes stable when we tune it. So to compare the parameters, okay here, and so we know that the parameter has been decreased from this to this, and then the integral also has been decreased. The rise time from 0 increased to 0.252, and then there's from the infinity overshots to 10.8 overshot. So we can say that the graph is stable after retuning. But the next one is PID controller. So same, you click here, then tune. So you come up with the result of this graph. So click here. So same. It's stated that the closed loop system with controller gain defined in the PID block is unstable and cannot be displayed. So you compare it here. And it shows the scope of PID controller just now. So this is very unstable graph from here, from the unstable graph to become the tune graph. So to compare the parameters, click here. Then here. So we know that the proportional gain has been increased, the integral gain has been decreased, and then the derivative also has been decreased. For the filter coefficient, it changed from 100 to 54.4431. Then for the rise time, it increased from 0 to 0.287. Then from the overshoot comes from infinity to 7.12. So the closed loop stability is stated as stable after retuning. That's all for my part. Thank you.
Hello and good evening. My name is Sailesh Anaraki Gopalakrishnan, seat number CE210068. I'm from Group 5. Today, I would like to explain about the result and discussion, which is the calculation for our project PID controller. So this is our main reference formula, which is GS equals to KP plus 1 over TIS plus D, DS and GS, KP bracket 1 plus KI over KPS plus KDS over KP. So we have compared the both equation. By comparing, we will get Ki equals to Kp over Ti and Kd equals to Kp and Td. This is our calculation to obtain Kp for P controller. So based on table 3.1, by using the formula Kp equals to 1 over A and substituting A by KL over T, we get 0.02, 0 times 0.01 over by 0.29, which is result as 6.896 times 10 to the power of negative 4. Therefore, when Kp is equals to 1 over A, which is 1 over 6.896 times 10 to the power of negative 4, the final answer will be 1450.116. And this is our calculation to obtain Kp and Ki for PI controller. Based on table 3.1 again, our Kp is equals to substituting the value 0.9 over A, which A is equals to 6.896 times 10 to the power of negative 4, and we will get the result as 1354.104. And Ti will be equals to 3L, which is 3 times 0.01. As a result, we will get 0.03. And as usual, Ki will be Kp over Ti, which is 45003.467. And the Kd will be, is 0. Hence, our GS is 1350.104 plus 1 over 0.03s. Next, we will look into the calculation to obtain Kp, Ki, and Kd. And for Kp, by substituting the value into the formula, which is 1.2 over 6.896 times 10 to the power of negative 4, as a result, we will get 1740.14. And for the Ti equals to L, by substituting 2 and 0.01, we will get 0.02. And for the Td, it is 0.01 over 2. As a result, we get 0.005. And for Ki, it is 1740.14 over 0.02, which is 87,007. And our Kd will be equals to Kp times Td, which is 1740.14 times 0.005, which is equals to 8.7007. Hence, our GS for this will be 1740.14 plus 1 over 0.02 seconds plus 0.05 seconds.
Hi, my name is Anshul Vidyalit. In conclusion, we have two model, a system in the MATLAB and Simulink software tool. We were able to test out the result of an open loop system and closed loop system. Before that, we have to design an appropriate system for transient response by turning to P, PI, and PID controller using PID and Simulink in MATLAB software. As for turning transient response, we choose to use transfer function, scope, speed, referent, and PID controller. And after that, we have to run the simulation. Then it will automatically appear on the correct graph. We set up our Simulink system and then tune it our value. Then we get the PID value. The observation from our discussion is that it has a long rise time and has many oscillation to get the desired output. That is for the PI controller result. Meanwhile, right, for the PID controller, it has a shortest rise time, which means it is a faster response controller. It also has fewer oscillation to get the zero steady state error, and it is stable than others. On the other hand, for the P controller, it does not have a zero steady state error, but it has better rise time of at output one episode around 0.6 seconds. Basically, from this experiment, we get to know in detail how to use the Simulink MATLAB software. We can adjust the value for dominant and numerator value in the transfer function parameter. We also achieve to come out the graph correctly from the transfer function, and we have a great. Last but not least, we can be a good groupmate in order to solve the problem by using any platform. We are also able to share and discuss about the experiment to be done.